Look at this wheel in the video. It's not designed for roads on Earth. It's designed for the moon. And it's built to jump directly into a pit that's tens of meters deep. The core idea of today's paper is mind-blowing. How can future lunar robots actually explore underground lava tubes on the moon? Now, you might be wondering, why bother going into these dark caves at all? Because the lunar surface is an absolute nightmare. During the day, temperatures scorch past 100 degrees Celsius. At night, they plummet below minus 180 degrees Celsius. And on top of that, you have deadly cosmic radiation and a constant rain of micrometeorites. But scientists discovered that inside these lava tubes, there's a sort of habitable zone, where temperatures stay relatively stable at around minus 20 degrees Celsius all year round. Even better, they could be the ultimate shield for future lunar bases, and the best place to hunt for underground water ice. But how do we actually get down there? Traditional plans rely on tethers and ropes. Picture a robot slowly rappelling down a cliff like a rock climber. But there's a massive catch. If the rope jams or the mechanism fails, the entire multi-million-dollar mission is toast. So this paper introduces a much bolder idea. What if we ditch the ropes entirely? What if the robot just jumps? The researchers realized that if the wheels themselves could absorb the entire impact of the landing, you wouldn't need a heavy deployment system at all. So what makes this wheel so special? Let's take a closer look. The genius of this wheel is its ability to do two things: collapse for storage and crush under impact. When stowed away, it's tiny, only 230 millimeters in diameter. But once deployed, it pops open to 500 millimeters. That's more than double its size. The payoff here is huge. It saves precious space inside the rocket during launch, but gives the robot massive obstacle-clearing power once it's on the moon. And this isn't your everyday rubber tire, nor is it a rigid metal wheel. Instead, it's a flexible, deployable structure. Inside, multiple elastic steel strips are woven into a beautiful spiral, lattice-like pattern. Most importantly, it has no traditional mechanical joints. No hinges, no bearings. And on the moon, that is a superpower. Lunar dust is notoriously sharp, abrasive, and gets into everything. Conventional joints easily get jammed and ruined by it. But this clever design has almost zero complex moving parts, making it incredibly reliable. What's even cooler is its unique mechanical behavior. When you fold it up, it's remarkably soft and easy to compress, kind of like a tape measure coiling up. But the moment it bears a vertical load, the woven structure locks together and becomes surprisingly stiff to support the robot. This is a property called anisotropy, meaning the structure changes its stiffness depending on the direction of the force. The ultimate goal here is incredibly ambitious. The researchers want a robot to drive right up to the edge of a lunar cliff and just drop off. Because the wheel doubles as both the tire and the suspension system, it cushions the landing completely. To prove this isn't just science fiction, the team put it through some brutal experiments. First up was the hot vacuum test. To simulate the harsh lunar day, they cooked the wheel in a vacuum chamber at 423 Kelvin for 24 hours. After pulling it out, its mechanical performance showed almost zero degradation. Then came the dramatic drop test. They loaded a testing rig to a whopping 9.3 kilograms and dropped it from a height of 770 millimeters. Now, less than a meter might not sound like much on Earth, but when you calculate the physics for a standard 4-kilogram rover under the moon's weak gravity, that impact is equivalent to surviving a terrifying 100-meter freefall down a lunar cliff. And guess what? The wheel kept working perfectly. No structural failure whatsoever. They also tested it in simulated lunar soil, using a special Korean regolith simulant, and proved the wheel gets amazing traction without getting bogged down in thick dust. In field tests, it easily rolled over 200-millimeter rocks and climbed up tough inclines. Ultimately, this paper redefines how we look at soft robotics in space. For a long time, people thought soft robots were too fragile for outer space. But this design proves the exact opposite. With the right materials and structural engineering, flexibility is actually a strength. By replacing complicated motors, joints, and actuators with the natural elasticity of a woven structure, you eliminate the points of failure. It's no longer just a wheel. It's a completely new philosophy for designing space robots.
If you enjoyed this, don't forget to like and subscribe so you won't miss more amazing robotics.